Magandang araw! Sama-sama tayong matuto sa Teacher Sal Learning Resource Channel. Revised K-12 Curriculum, Science 5, Quarter 3, Week 5, Static Electricity. Let us recall our previous knowledge. Matter is made up of atoms, and atoms are made of what particles? The proton, the electron, and the neutron. Let us establish that protons are positively charged and electrons are negatively charged. The neutrons, on the other hand, contain no charge. Figure 1. The Bohr model, a model of an atom displaying the nucleus, electrons, and orbiting paths of electrons. Figure 2. Figure 3. If pairs of objects are held near each other, as shown below, do they attract or repel each other? Every atom consists of negatively charged electrons surrounding a positively charged nucleus. As indicated in Figure 3, the nucleus is made up of positively charged protons and neutral neutrons. Electrons can migrate between atoms, molecules, and materials. Most objects lack an electric charge because the material they are made of contains an equal number of electrons and protons. In certain situations, there may be an imbalance of protons and electrons. An object with more electrons than protons is negatively charged. An object that has more protons than electrons is positively charged. Repel, attract, repel. What is the result when a negative charge is placed near a piece of foam with no electric charge? Nothing happens because the foam does not have a charge. What is required to keep two positive charges close together? An external force has to be applied to both of the charges to keep them close together. What causes an object to become positively charged? Rubbing off electrons from an object causes the object to become positively charged. This is because electrons are free to move and be removed from an object, while protons in the nucleus are pretty much bound inside the nucleus. Think pair-share. Begin to develop an idea of what a field is in a physics context, as well as what properties a field has. In Charges and Fields, students explore electrostatics as they arrange positive and negative charges, space, and observe the resulting electric field, voltage, and equipotential lines. Stink field analogy from physics classroom. Imagine this. There is something smelly in one corner of the room. Maybe a rotten egg or a dirty diaper. Think about these questions. When you enter the room, how do you know something smells bad? Does the smell change depending on where you stand in the room? When you move closer to the smelly object, what do you notice? If the object smells really bad, how can you tell right away? Answers will vary. Stink is stronger, closer to source. Moving slightly tells the direction of the source. A more rotten egg smells worse. A bigger stink field. Don't have to see it to detect it. Does your nose change the properties of the rotten egg when you smell it? Nose just detects, but doesn't change the amount of stink, just records. A poopy diaper is known to alter the olfactory properties of the surrounding space. It creates a stinky field that permeates the surrounding space. Without ever contacting the diaper, every nose in the room knows that the space has been altered by the presence of a stinky field. And the strength of that stinky field depends on how close you get to its source, the diaper, and the amount of stink in that source. Stinky field versus electric field. A nose is used to detect a stinky field. Another charged object, test charge, is used to detect an electric field. The detector is interacting with the field, not with the source. The strength of the field varies inversely with the distance from the source of the field. The strength of the field depends upon the properties of the source, the amount of stink or charge on the source, the information. As you move closer to a charged object, the strength of the electric field increases, and as you move farther away, the strength decreases. This is because the electric field emanating from a charged object follows an inverse square law, meaning it weakens proportionally to the square of the distance from the source. Therefore, the closer you are to the charged object, the stronger the electric field you'll experience. This relates to the concept of field properties discussed in the experiment by highlighting how the electric field's strength varies with distance, a fundamental characteristic of fields in physics. Atom. It is the smallest unit of an element, consists of a dense, positively charged nucleus surrounded by electrons. Molecule, the smallest particle of a substance that retains the chemical and physical properties of the substance and is composed of two or more atoms. Electron, the negatively charged particle of an atom. Proton, the positively charged particle of an atom. Neutron, the neutral particle in an atom. Nucleus, the positively charged central region of an atom composed of neutrons and protons. Static electricity, the buildup of charge on an object or the spark that is a result of a buildup of charge on an object. Fill out the table below to tell us what you think and what you want to know about it. Later on, when we are done with our lesson, we will be answering the last two columns. For day 2. Can you stick a balloon to a wall without using glue or tape? Activity number 1, imaginary shelf. Blow up 3 or 4 balloons. Wrap the balloons against your sleeve or shirt as if cleaning them, then stick them to the blackboard in a horizontal row. Once you notice what happens when you rub the balloons, rub the other balloons on your hair or shirt and try to make a second row of balloons below the first row. How are the balloons sticking to the board? When you rub a balloon against your sleeve loses some electrons. The balloon ends up with extra electrons, making it negatively charged. When the negatively charged balloon approaches a wall, the negative charges in the wall are repelled or pushed away. This leaves a positive charge on the wallboard at the spot where the balloon touches. What did rubbing against a sleeve do to the balloon? It is the attraction between the positively charged area of the wall and the negatively charged balloon that results in the balloon sticking to the board. Over time, electrons will transfer from the balloon to the wall, causing the balloon to become uncharged and fall to the floor. Do the balloons stick to the wall forever? Why or why not? Some materials lose electrons more easily than others. The more easily the material loses electrons, the better it will charge up the balloon. Wool, cotton, and hair are the most effective materials to charge the balloons. For day 3. Activity number 2, balloon electroscope. Blow up 2 balloons to the same size and tie a thread to each one. Hold the 2 threads together so the balloons hang touching each other. Have a classmate hold the threads while you rub both balloons with a wool cloth. Let the balloons hang again. This time, the balloons will not touch. Spray a light mist of water on the balloons. They will fall back and touch each other again. Why do the balloons repel each other after rubbing? Why do the balloons fall back against each other after spraying? How else could we get the balloons to fall back against each other? During what type of weather would it be best to do experiments on static electricity? What does damp weather do to the electric charges? Positive and negative charges attract each other because they are opposites. But what happens when something charged is near a neutral object? In this activity, you will observe what a charged object does to materials that have no charge. Lesson activity, interactive discussion. Part 1. Picking things up. Try different ways to charge your balloon. Rub it on your head, your clothing, or other materials to see which works best. Slowly bring your charged balloon near the confetti and watch what happens. Record what you observe in your notebook. Look around the classroom and test what other small items your charged balloon can attract or pick up. Part 2. Moving a stream of water. Turn on the tap so that you have a slow, solid, steady stream of water. Take turns slowly moving a charged balloon towards the water and observe. Be careful not to touch the water. Part 3. Challenge. How far can you move a pop can with a charged balloon? With your team, work together to try and move the pop can using only charged balloons. No touching the can with the balloons. Roll out a measuring tape on the floor. How far can you get your can to move before the balloon loses its charge? What happens to the confetti when you hold a charged balloon near it? Why? What happens to the stream of water when you move the charged balloon near it? Why? What happens if you let the balloon touch the water? Can you get the can to move? How about tip over? Hint, try moving the can when it is on its side. For day 4. Go back to the TWLH chart. Reflect and check if your answers in the think column are correct. Accomplish the learned and how column. Why do you think that your hair stands up after rubbing it with a balloon? Electrons move from your hair to the balloon. Then each of the hair has the same positive charge. Since objects with the same charge repel each other, the hair try to get as far from each other as possible, which is by standing up and away from the other hairs. What are some examples from your own experiences of the buildup of discharge of static electricity? Walking across the carpet, buildup, and touching a doorknob, discharge. When you walk across a carpet, electrons rub off the carpet onto your shoes. When this happens, which becomes negatively charged? The carpet of your shoes? Shoes. Make a drawing of what happens to the charges on a wall when you touch a negatively charged balloon to it. Here is the possible answer. Describe an example of static electricity. Clothes sticking together when removed from the dryer. Lightning, the shock you feel when you touch an object after walking across the carpet.